Everybody hear me okay? Just testing out the mic. We are about a half a minute away from the top of the hour. Just put on the recording. So, welcome to everybody. This is class number 15 for college geometry. And you know what that means, folks. This is the final class for this course. I want to wish everybody a very happy holiday season. I know we still have one class to go, and that's this class. It also means that the final exam will be posted today. I'm not sure if it might already be up. I don't remember exactly when I had it posted for. If it's not up yet, it should definitely be up within the next hour or so. It will be similar to exam number 1. If it's not up yet, hopefully, let me check to see exactly when it will be posted. I will tell you right now as soon as I check on it. But it will be similar to exam number 1. It will ask you to do work on graphing, work on, let's see, what else did we cover in the second half of the course? We covered circle geometry, we covered graphing, we covered basically, everything from class 9 forward. So actually, let me quickly look and just see over here exactly when the exam will be posted. Okay, it'll just take me a second to look this up as soon as the system responds. All right. Okay, there we go. I have it scheduled to go up at 7:30 today, so at 7:30 Eastern, which is in about an hour. So by the time class is over, you'll be able to take the exam. If you want to take the exam before the holidays, I think that would be a fantastic idea. The material is fresh in your mind. If you're not comfortable taking it yet, that's perfectly okay. You don't have to take it. The course deadline's in about a month from now. I forget which day, although I'm going to hazard a guess that it is January 24th is probably the deadline for the course. In any case, that, of course, for those of you who are listening to the recording and for those of you who are here, I want to ask everybody to please get going on your work if you haven't already done so. If you've done already a few assignments and an exam, I think you're in excellent shape. If you have not gotten very many assignments in, if you've only gotten like 1 or 2 or 0 assignments in and you haven't done an exam, you don't have a lot of time left. I know it's the holidays, and I know people don't really like to, do work during the holidays if they can avoid it, but this would be a great time to start on the work if you can at all. Remember, the deadline for the class is January 24th. You can take an extension for a grade penalty, as is discussed in the course syllabus. I really ask everybody to please try to not do that. I'll grade everything as quickly as I can, generally speaking, when people submit things. However, again, I implore everybody to please not wait for the last minute to get your work in. If you're a little behind, that's okay. You still have a little bit of time, but please try to catch up. Don't wait until January 15th or January 20th and then start worrying about homework number 2. That's just not a very good strategy. Okay, with that in mind, today we're going to discuss transformations, and I've got good news for you. Transformations are easy. Transformations are probably one of the 15 different subjects that we've covered in this course. I would say transformations is probably among the 2 or 3 easiest. Because transformations, all you're really doing is you're taking things from one part of a graph and you're putting them in other parts of a graph. Last week we discussed harder things about graphs. Last time we discussed how to write equations for circles and how to write equations for lines, how to solve equations that, systems of equations using graphing. We also discussed things like figuring out slopes and figuring out perpendicular lines, parallel lines. That is more complicated than transformations. Today we're going to discuss transformations, which is simply where you take a point or take a shape or take something and just kind of move it to a different section of the graph. Transformations in general assigns every part of a point to another point in accordance with a particular set of rules. Those rules could be that you're making the x negative, it could be you're making the y negative, it could be that you're moving it over 5 spots, it could be that you're moving it up 5 spots, it could be that you're moving it over 5 spots and up 3 spots. Whatever rule you establish, you then can go ahead and apply. And of course, just like when you're talking about in real life, when you have to move a structure because you made one set of plans and because of some environmental, drainage problem or whatever, the building cannot be built on that spot. Well, the building might have to be moved over a certain distance. That doesn't mean the building necessarily changes. That doesn't mean the size changes. That doesn't mean the shape changes. In fact, in most of the transformations that we are going to be discussing today, very little changes about the shape. The only thing that really changes about the line or shape in most of the transformations that we are going to be discussing today is the position. It moves over a little bit, it turns around a little bit, it rotates, whatever transformation it makes, but the figure itself in most of the transformations that we are going to discuss just stays the same. Each type of transformation has its own set of rules and characteristics, and we're really only going to cover about 4 or 5 of them. And the way these things are labeled, if ABC, let's say a triangle with point ABC, then when you do the transformation, the result of the transformation is used with one of those little apostrophes, which in math is called prime. So A, B, C would turn into A prime, B prime, C prime. That's just a method of naming. As we discuss it in this class over the next 55 minutes or so, I'm just going to be discussing, okay, well, this is point A. After the translation, or after the rotation, or after whatever transformation we're trying to discuss, the result is going to be A prime. There are 2 types of transformations that we're going to discuss. One is an isometry. An isometry preserves distance, congruence, etc., which means the shape is the same as it was before the transformation. That is what basically all of the transformations that we're going to discuss today, except for one of them, maintains congruence, maintains distances, maintains pretty much everything. In other words, the size and the shape and the characteristics, and those are called isometries. The last one we're going to discuss today is not an isometry, but a similitude. What is the root of the word similitude? Well, hopefully you could tell that the root of the word similitude is similar. It maintains similarity, but not the exact shape. That's what we're going to discuss later on when you have a dilation. A dilation is when you make something bigger or when you make something smaller. When you make a shape bigger, but you keep the shape, it is similar. In other words, the dimensions are in proportion, but it is not congruent. It is not the exact same thing. So those are the general rules regarding the transformations that we are going to discuss today. Our very first transformation is a very simple transformation called a translation. A translation simply moves the figure from one area to the next. Is this a similitude, by the way? A translation, if you look in the graph in the lower right-hand part of the page over here, where you got this is a quadrilateral, this is a quadrilateral. Is this any particular type of quadrilateral? I don't know. I don't think it's any of the types of quadrilaterals. Like it's not a trapezoid or or a rectangle or a parallelogram or anything like that. But it is a quadrilateral, and we're moving it over. And yes, this is an isometry. And the reason why it's an isometry is because the original shape EFGH, quadrilateral EFGH, is moved into F prime G prime H prime E prime, or F prime E prime H prime G prime, either way. That it is the same shape in terms of distances between the sides. It's the same shape in terms of congruence. These 2 quadrilaterals, as you can see just by looking at them, are congruent to each other. Is EF the same distance as E prime F prime? Well, of course it's yes. You can just count it. 1, 2, 3, 4 over. How about EH? Well, EH, you'd have to use the distance formula to figure out the distance of EH. EH would actually be the square root of 10, I believe, is the distance between E and H, just the square root of this squared plus the square root of this, plus this squared. So I think the square root of 10, which is about 3.3 or so. So EH is the same distance as E prime H prime. Notice, of course, EH also goes down 3, 1 over, just like E prime H prime goes down 3, 1 over, just like EH goes down 3, 1 over. Okay, this is a translation. A translation just means it is moving. What is happening to each point? Well, each point in this case is going down 6. I'm sorry. This is actually a mistake. This is a mistake. You know what mistake do I have over here? What mistake did I make over here on this piece of paper? This is not a translation. Well, first of all, let me get rid of that arrow over there. Right, exactly. This is not a translation of -6, -3. It is actually a translation of -3, -6. Because the first thing is always the x value. The x value is changing 3, and the y value is changing 6. Let's take, for example, e. E to e prime goes 1, 2, 3 over. 1, 2, 3, 4, 5, 6 down. 3 over left, which is a -3 change, and it's a -6 change. Of course, it started at e and ends at e prime. So it's a -3, -6 change, and of course all the others have the exact same change. If you want to get h to h prime, you also have to go over 1, 2, 3, and down 1, 2, 3, 4, 5, 6, and you'll get to h prime. And the same thing, of course, is with f to f prime, 3 over, 6 down, and g to g prime, which is 3 over and 6 down. Okay, I know that looks a little messy, but hopefully I've at least demonstrated that this is a classic -3, -6 translation. How do I know, by the way, just looking at this stuff over there, how do I know that this is a -3, -6 translation rather than a +3, +6 translation? I guess it really depends on which way you look at it, but the answer is the one without the prime is the initial shape. The EFGH in the upper right-hand corner in quadrant 1 is the initial shape because it has no primes. The other shape, which is kind of bleeds from quadrant 3 into quadrant 4, is the one with the primes. That is after the translation. So that's simply a translation. You move over each point by a certain x value and by a certain y value. Okay. Now you've got a rotation. A rotation simply transforms the figure around a fixed point. Now, a rotation could be 180 degrees, which means you're flipping it upside down. A rotation could be 90 degrees clockwise, or a rotation could be 90 degrees counterclockwise. Let me put this over here so that we can open a nice Microsoft Paint thing over here. All right. Just give me 1 second. Okay, can everybody see my Microsoft Paint over here in my browser? Okay, very good. Let's say we've got, let's do all 3 types of rotations over here. 180-degree rotation, a clockwise rotation, and a 90-degree rotation. To make it simple, rather than doing a quadrilateral, let's do a triangle. So we'll put point A here at 2, 2. We'll put point B here at 6, 2. This was at 2, 2. And we'll put point C here, which is at 4, 1, 2, 3, 4, 5. And this is point C, and this is at 4, 5. And let's make the triangle. We'll make the triangle using line segments. Actually, let's use one a little bit thinner than that so it doesn't overwhelm everything. Okay. Okay, this is our A, B, C. Okay? All right, let's use a different color. Let us now flip it around let's do it clockwise. Now, clockwise means to the right. Clockwise means circling it around in this direction. Okay, now, if you flip the triangle on a 90-degree rotation, basically, let's pretend that you took the entire computer screen and you turned it on its side, like a clock. Imagine the hour hand of a clock going from 12 o'clock to 3 o'clock. What happened? Basically, you went a 1/4 turn. Now, what do you think would happen? You know, I have an idea. I have an idea. Let's use Paint to actually rotate it for us, and then we'll have a better idea about why it happened. Okay? Or can everybody see the triangle at this point? I'm going to rotate right 90 degrees. Rather than drawing it ourselves, we can actually rotate the whole thing right in 90 degrees. 1 second. Okay, that went. Whoa. 1 second. Okay. I don't know why it decided to. Okay. Sorry. I don't know why it decided to put it on the wrong side of the page. But does everybody see what happened when we rotated it 90 degrees? Well, it's as though you took the entire diagram and flipped it on its side. So let's go back to the example. And this time, let's draw a 90-degree rotation. What's going to happen to A? Where should we put A? At A prime, excuse me. On a 90-degree rotation clockwise. Where should we put A prime? Assuming the whole thing gets flipped around to over here. Well, A prime is kind of the focal point. So A prime can be over here, right? Because when you flip it on its side, A prime is still going to be over here. Where's B prime going to be? So A prime's over here, and that is at 2, -2. Where's B prime going to be? Remember what happened when we flipped it over? 2, -6. Exactly. That's 100% correct. We're going to put 1, 2, 3, 4. B prime over here at 2, -6. Again, because it kind of flipped on its side. And let's draw our little line between 2 points. Okay. Now, where is C prime going to be? If you flip this triangle over, where is C prime going to have to be? C prime is going to have to be over here, right? Look, like for example, this was 4 squares up from the middle over here. So if we do the same thing over here on its side, we can put C prime over here, just following the same rules as the triangle up here. And this is point 1, 2, 3, 4, 5, 6. 1 second. Oh no, I'm sorry. This is, I put it in the wrong place. It'll be over here, because this was 3 squares up. Okay. So C prime would be at 5, -4, exactly. Okay, so that's 5, -4. Let's draw this to here, and this to here. Okay. It doesn't look that perfect. I think it's because these squares aren't perfectly drawn. I think when I expanded and contracted the drawing a little bit, I think these squares aren't perfect squares. But anyway, assuming they were perfect squares, this would be an example of taking the entire graph and flipping it 90 degrees in that direction. Okay, what about the other way? What about if we wanted to flip again clockwise? We wanted to take this and we wanted to flip it to the 3rd quadrant. This time I'm going to make it green. If we were to take this, take A, and flip it to the 3rd quadrant, take this entire thing and flip it over here. What's going to happen to A? We'll call it A double prime. Yeah, A double prime is still the anchor. So A double prime is still going to stand over here. We'll call this A double prime. A double prime is at -2, -2. Okay. What about B double prime? B double prime is going to kind of swing like this. It's just move over on another 90 degrees. So B double prime is going to be over here, which is -6, -2. How about C double prime? Well, C double prime is going to flip in the same way to around here. 1, 2, 3, 4, 5. Again, it's going to preserve the same distances. So C double prime is going to be -5, -4, -5. Okay. Let's draw our green double shape over here. Alright, now, I got a question for you. What is the relationship between the black triangle and the green triangle? That's 180-degree rotation. Exactly. This is essentially what would happen if you flip the whole thing upside down. If you did flip the whole thing upside down, I think Paint allows you to do that also. 180 degrees. Oh, there we go. Okay, I could just move it over. There we go. Notice how it looks. Now, forget obviously the reddish one would be in a different quadrant, but notice how the green and black ones just kind of flip places. They're the exact same thing as they were in the last one, but just they're different colors. The green one is where the black one was, and the black one's where the green one was. That is a 180-degree rotation. So, based on this, can anybody tell me what happens in a 180-degree rotation? In any 180-degree rotation, I'll write it down over here. In a 180-degree rotation, you have x, y becomes -x, -y. Right? A was 2, 2, it became -2, -2. B was 6, 2, it became -6, -2. C was 4, 5, it became -4, -5. Actually, there should be a negative over here. I didn't see that, but anyway. Oh, okay, I put that in the next slide. Excellent. Well, there we go. That's let me use the bigger, just like the one that we did over here in our diagram. The same thing is true with the one on the slide. The one on the slide we had A prime B A B C. A was at 7, 4. B looks like it's at 6, 1. C is at 3, 1. And A prime B prime C prime is at -7, -4, -6, -1, and -3, -1. When you go flip 90 degrees clockwise, the y value they flip order, and you have the x becomes negative. When you flip counterclockwise, they flip the order, and the y value becomes negative. Now, you have two choices when you're doing a question like this. Either A, you can memorize this procedure, and you could say if it's clockwise, well then they flip, instead of being, let's say, 2, 4, it would become 4, -2. And for counterclockwise, it would be -2, 4. Or you can just look at it from a logical perspective and try to draw it and try to envision what happens when you have a rotation. Let's go back to let's go back to this one over here. I want to demonstrate that. Okay. Sorry, the screen sharing went. Okay, can you see the screen sharing? Can you still see the screen sharing over here? No, this is not the right screen sharing. Oh, okay, I know why. I know what happened over here. Just give me 1 second. All right, there we go. Okay, I'm sorry. Screen sharing wasn't working for a second there, but that should help. Okay, there we go. All right. Now, okay. So now let's take a look at the counterclockwise. I'm sorry, the clockwise rotation. We're from the black triangle to the reddish triangle. Well, xy becomes y negative x. So let's take, for example, C, which was a 4, 5, became, well, the y is first this time, so it becomes 5, and the x value becomes negative. So it becomes 5, negative 4. And of course, you can see that's what happened. The 4, 5 turned into 5, the negative 4. So you can look at it, try to picture what would happen if it flipped 90 degrees, or you could remember this formula that xy becomes the y goes what was before the y value becomes the x value, and what was before the x value becomes the y value, but it has to be negative. Now do our fourth one. Let's do our fourth quadrant. This time we'll make it purple. Okay. Now our fourth quadrant, what kind of a rotation are we doing from the black triangle? From the black triangle for our fourth one, what kind of a rotation are we doing? Here we're doing 90 degrees counterclockwise, right? Exactly. Okay. Now what's our rule? Our rule is that xy becomes negative y x. Okay. So what does 4, 5 become? What does C become? The y goes first in its negative value, so it becomes negative 5, 4. Okay. What does the b become? From 6 to 2, it goes to negative 2, 6. And the a, which was 2, 2, well, simply becomes negative 2, 2. Okay. So a becomes negative 2, 2. That's it. This, and we'll call it a triple prime because there are 3 of them by now. B became negative 2, 6. Negative 2, 1, 2, 3, 4, 5, 6. This is B triple prime, and C triple prime. C triple prime became negative 5, 4. Negative 1, 2, 3, 4, 5, and negative 4. This became C triple prime. And let's draw this rotation. Okay. There we go. Okay. So now we've got really the exact same shape, but rotated into all four quadrants. Now, of course, notice that this triple prime one, the purple one, it's a counterclockwise rotation from the black one, from ABC. It's also a clockwise rotation from the green one, and it's also a 180-degree rotation from the dark red one. See how it's all pretty much the same thing? And that's also like the diagram on the slide. A, B, C, and D are just 4 of the same shapes. They're all congruent to each other. They're just in all different quadrants. For example, you could say that A is a 90 degrees clockwise rotation from B. Excuse me. B is a 90 degrees clockwise rotation from A. It's a 90 degrees counterclockwise rotation from C, and it's a 180 degrees rotation from D. All of those, of course, would be accurate. Okay, let's go to the next one. Let's set up a graph here. Why is this graph coming out so big? I don't know. This is not going to work. What if I do this? Alright, good enough. This will have to do. Okay, let's discuss a reflection now. And before we do, and let me get the big slide up here. Okay, a reflection is very similar to a rotation, except that instead of moving around, it's kind of flipping around like a mirror. Imagine any line being a mirror. Right, and so a reflection could be in an axis. A reflection could be in a different type of line. So this transformation brings the figure to the opposite side of a particular line. The reflections preserve congruence. Obviously, if you look at the diagram, you look at the top diagram over there, what is this being reflected in? This diagram over here, the top one on the slide. AC is being reflected to A prime, B prime, C prime. What is it being reflected in? The answer is it's being reflected in the y-axis. Do you see how A is A prime's mirror image being reflected in the y-axis in this line over here? B flipped over the y-axis, and C flipped over the y-axis. Basically just make the x value and keep the y value as it is. 2, 2 became negative 2, 2. 4, 4 became negative 4, 4. And 5, 1 became negative 5, 1. What if you would flip it in the x-axis? Then what would happen? Then it would be the x value that would stay the same, and it would be the y value that would change. Exactly. 2, 2 would become 2, negative 2. 4, 4 would become 4, negative 4. And 5, 1 would become 5, negative 1. And the triangle would be the mirror image, and something to that effect. Reflection in the line, again, a little bit more complicated, but the same basic idea. This is an example of a reflection in the line y equals x. Y equals x is this purple line over here that goes through the origin. Notice, by the way, what's the slope in the line y equals x? Is this mx plus b form? Right, and it is y equals mx plus b form, just there is no b, so b is 0. So it's y equals 1x, which means the slope is at 1, and the slope is here 1, 1 up, 1 over, 1 up, 1 over, 1 over, 1 up, 1 over. And there's no y-intercept. The b is 0. Because the b is 0, so the y-intercept is 0, which means it passes through 0, 0. It passes through the origin. To flip one or the over, to flip this quadrilateral into this quadrilateral, or vice versa, just flip them. Make the x into the y value and the y into the x value, based on the mirror image. B was 0, 2. It becomes 2, 0. C was negative 3, 1. It becomes 1, negative 3. Basically, you're taking xy and just changing it into yx. I don't want you to have to remember that, because again, there's a lot of, if you try to memorize them all and try to say, well, if you reflect in this, then, the x becomes the y and the y becomes the x, and this becomes negative. Then it becomes, just memorizing a whole bunch of formulas. You don't need to memorize a whole bunch of formulas. What you need to do is be able to just look at it logically and say, what should happen if I take the C and flip it over? Does that mean you cannot use these conversions? You can. If you're taking a test and you're not sure what it would look at logically and you want to look at one of these conversions and use that conversion to make it, you can do that. That's fine. Nothing wrong with that. But I'd like you to know the logic in terms of why C turns into this C prime when it's being reflected over this purple line, rather than just memorizing the x and y get flipped into yx. Because you're taking this, and the mirror image is this. Notice one interesting thing, by the way. When you're reflecting something in a line, the distance from each point to the line stays the same as its opposite. The distance from C to the line is the same as the distance from C prime to the line. B to the line, B prime to the line. A to the line, A prime to the line, always are going to have the same distance. That's characteristic of a mirror. When you look at yourself in the mirror, everything looks pretty much the same, except it's on the other side. That's really what a reflection is, kind of a mirror. Okay. And finally, our last transformation is the only one that is not an isometry. This is a similitude. The line is the yes, that is true also. Devore points out that the line is a perpendicular bisector of each line between its line of Okay. Sorry about that. Alright, we're back. Alright, I apologize for that. Alright, so let's take a line. Let's see, is there any way to make a straight line over here? Well, alright, there's not exactly a straight line, but it'll have to do. You draw this reddish line from C to C prime. Well, this line is bisected by the purple line. And as you can probably also tell, it's perpendicular to the purple line. This would make a right angle. Okay. Simple enough. A size transformation is a similitude, but it is not an isometry. Which means that then this is what's called a dilation, or a size transformation. Which means you're making something bigger, or you're making something smaller. If you're making it bigger or smaller, you can write it down with like a D, which stands for dilation, and in parentheses you put what each one is multiplied by. 2, 2 means the x is multiplied by 2 and the y is multiplied by 2. They don't necessarily have to be the same. It could be 2, 3, or it could be one quarter. Okay, I'm sorry, I'm having a little. I'm sure my sound is cutting out a little bit. Do apologize for that. All right. Okay. So let's say, for example, over here, in this diagram over here, we've got ABC, which is the pink triangle, and we've got A prime, B prime, C prime, which is the blue triangle. Now, this is a 2 times dilation. D2 means the A is getting multiplied by 2, and the X value is getting multiplied by 2, and the Y value is getting multiplied by 2. For example, let's take point A. Point A prime is negative 2, negative 2. That means point A is negative 2, negative 2. That means that point A prime is each one multiplied by 2, which is negative 2, negative 4. B is 1, negative 1. That means B prime is 2, negative 2. C is 2, 0. Well, you multiply 2 times 2 is 4, but 0 times 2 is still 0. So C prime is 4, 0. Now, question. Are these triangles similar? Are their sides in proportion? The answer is yes. Any kind of dilation you're going to do, you're going to maintain similarity. Now, in this case, I think this is pretty obvious, but what is the relationship between the sides in terms of distances? Okay, double. Everything is twice as big over here. The area is actually, I think, going to be more than twice as big. Should we figure out the areas here? Yeah, let's figure out the areas of both triangles. Are these right triangles? Let's figure out, by the way, let's figure out if these are right triangles. Honestly, they look like right triangles, but we're going to figure out whether they're right triangles over here. Okay. CB has what slope? What's the slope over here? It looks like 1, 2 over 1, 2, 3, 4, 5, 6 down. So the slope looks to be -3. Okay? So BC's slope is negative. See how I got that? See how I got the slope? 1, 2 over 1, 2, 3, 4, 5, 6 down. So that's a slope of -3. What is the A prime B prime slope? Well, 1, 2, 3, 4, 5, 6 over 1, 2 up. So that's positive 1/3. So are those right? So are those in other words positive 2, 6, which is the same thing as positive 2/3. So are those are those perpendicular? The answer is yes, because they've got negative reciprocal slopes. If AB or A prime B prime is positive 1/3 and C prime B prime is -3, those are negative reciprocals of each other. So those are perpendicular. By the way, what about the pink one? Is that also going to be perpendicular? Well, the answer is yes, it has to be, because they're similar triangles, and similar triangles have the same angles. By definition, that's what a similar triangle means. They have all three same angles. And of course, if we count, we'll confirm that very easily. AB has 1, 2, 3 over 1 up. That's a 1/3 slope. And CB has 1 over 1, 2, 3 down. That's a -3 slope as well. Obviously, they have to have the same slope. So to figure out the areas, we can do base times height divided by 2. Since this is a right triangle, we could figure out the base. What's the distance between A and B? Well, let's use the distance formula to figure out the distance of the pink one. Let's do the pink one first. I'll do it up here. The pink triangle will do. Let's do AB first. The distance of AB is the square root. Remember, the square root of x1 of x2 minus x1 squared. That's 1, 2, 3 squared. That's 9. Plus the difference between the y, which is 1 squared, which is 1. So AB. Okay. So this is the square root of 10. That's the difference between AB. How about CB? Looks like the same thing, doesn't it? It's also 1 over 1, 2, 3 down. So this is also the square root of 10. CB. By the way, so what's the area of ABC? Well, it's the square root of 10. It's base times height divided by square root of 10 times the square root of 10 divided by 2. Square root of 10 times square root of 10 is 10. 10 divided by 2 is 5. So the area of the little triangle is 5. How about the area of the blue triangle? Let's do that over here. Let's do the area of the blue triangle. Okay, so let's figure out A prime B prime first. A prime B prime, square root of the change in x, which is 1, 2, 3, 4, 5, 6, which is 6 squared, plus the change in y, which is 1, 2, which is 2 squared. So AB equals square root of 36 plus the square root of plus 4. So A prime B equals the square root of 40. And what about B? C prime, of course, is the same thing as, it's the same distance, 2 over. So the area of the whole blue triangle of A prime, B prime, C prime is the divided by 2, which is 20. So, what does that say about the area of the two triangles? Notice this was a 2-point dilation, a 2 times dilation, and yet the area was 4 times as big. Why do you think that is? The answer is because it is two-dimensional, right? If it's two-dimensional, both dimensions were being multiplied by 2. That made the area be twice as big in both directions, exactly. So what if I had this, by the way? What if I told you to make a dilation in 2 and 3? In other words, the x value was multiplied. The area would multiply by 6, because this would be multiplied. This distance, the x distance, would be twice as big. The y distance would be 3 times as big, and because they have to be multiplied by each other, that would be 6 times as big altogether. That's why, imagine you have a box that's 5 by 5, and another box that's 10 by 10. The box that's 10 by 10 is going to be 4 times as big as the box that's 5 by 5, right? The box that's 5 by 5 is 25 square feet, if it's 5 feet by 5 feet. And the box that's 10 by 10 is 100 feet, which is 4 times as big. All right. Let's take a look at some examples here. All right. There we go. Okay, who wants to help me with this one? Look at this shape. Which shape shows a translation? And don't just tell me the answer. Tell me why. Which one is a translation? Not a rotation, not a dilation, none of those things. Just a translation. It's moving, but it's not being rotated, and it's not changing its size. Well, the answer is C. That's correct, because A is a rotation. What kind of rotation is A, by the way? A looks like a 90-degree rotation clockwise, kind of shifted over clockwise. B looks like a 180-degree rotation. C looks like a translation. The whole thing kind of shifted over a little bit. What kind of a translation is it? Oh, it looks kind of like it went back 1, the x value, and the y value went up 1. It looks like a -1, -1. Looks like a -1, translation. Excuse me. Right. Okay. B is a reflection. That is correct. B is a reflection. Yes. So we're going to say C, and we're correct. Excellent. Okay. Which image shows a rotation? Well, let's see. What does A show? A shows a translation, right? Just kind of moving the whole thing over. What does B show? B shows a reflection. It's just kind of flipping over whatever this middle line is over here. C, on the other hand, Looks like a rotation. What kind of a rotation? Looks like a 90 degree in which direction? Counterclockwise, because you're kind of shifting it upwards on its head a little bit. Okay. Look at this shape. Which image shows a translation? Well, what does A show? A looks like a reflection in the middle horizontal line is, kind of flipped over the middle line. B shows a rotation, a 90 degrees counterclockwise rotation. C does look like it shows a reflection, 1 over and 1 down. So a positive 1, negative 1 reflection. Why are they all C? Huh. Okay. Which shows a rotation? Okay, well, let's see. What does A show? Shows a translation. It looks like a positive 1. I'm sorry, the X, yeah, positive 1 rotation. B, what kind of a rotation is B? 180, that's right. That all the way rotations or 180 degree rotation, flip all the way around from quadrant 1 to from quadrant 3 to quadrant 1. If you carefully, you'll see that they're really the same thing, just taking up a different quadrant. What about C? What does C look like it is? C looks like it is a reflection in the horizontal line over here. Okay, which image shows the rotation? Alright, these are getting pretty repetitive, but we can look at a rotation over here. Okay, what kind of a rotation is A? Interesting one. It is A, but what kind of rotation is that? It's a full 180 degrees, that's right. A little harder because it's bleeding into different quadrants, but if you took this entire thing and flipped it over, that's what you'd get there. B looks like it is a reflection in the horizontal axis, and C looks like just a regular translation. Alright, okay, fine. I think we've seen enough of these. Alright. How about this one? These are a little bit more complex. Okay. Let's do the ones with graphs. Without graphs, it's just memorizations. Let's do the ones with graphs. Okay. The wrong answer is still in here. so let's figure out which one it is. Which of the following transformations is illustrated by the graph on the right? Is it a dilation, a reflection in y equals x, that's a reflection in the line, y equals x, a translation, or a reflection in the origin? A reflection in the origin means it reflects in that middle dot over here that's 0, 0. Okay, well, let's take it one at a time. Is this a dilation? No, it's not a dilation, because dilation would change the size. And these two triangles are the exact same size. They're each square root of 1 by the square root of 2 by the square root of 2. Reflection in y equals x. It's not a reflection in y equals x. Reflection y equals x is a line that goes over here, so negative 2, negative 1 would turn into 1, negative 2. It would kind of be more over here. It's not a translation either. Translation wouldn't change orientation, whereas this does change orientation. It changes side. This is a reflection in the origin. Reflection in the origin, the x becomes negative and the y becomes negative. Negative 2, 1 becomes 2, negative 1. Kind of imagine this one point in here was the middle. was it was being reflected in this. It's a reflection in the origin. Okay, number 3 is easy. In the translation of 3 and 2, what does 2, 5 become? Is it a rotation? Is it also 180-degree rotation? It looks like it is also 180-degree rotation. As a matter of fact, I think 180-degree rotation is the same idea as a reflection in the origin. If you took this and you flipped it around 180 degrees, yeah, let's get that same thing. Okay, so just add the 3, 2. Translation just means add 3 and add 2. So 2, 5 becomes 5, 7. That's a pretty simple. Why? Which one? Number 2? No, I think it's correct. Okay, you'll let me know. All right. Symmetry we didn't really discuss. How about this? How about number 6? Which of the following descriptions is true? Double prime, B double prime, C double prime, which is the quadrant 3. No, a reflection in the origin it means reflection. It doesn't mean rotation. It would be a 180-degree rotation. That's the same thing. But a reflection, it's possible to have a reflection in a point. That in today's class we kind of discussed reflection in a line, but it's also possible to have reflection in a point, which is the same thing as a 180-degree rotation. Basically, rotation in a point is the same thing as a 180-degree rotation around that point, if that's possible. I mean, well, it's possible, obviously, but if that makes sense, I guess. All right, number 6. Which is true? A, B, C, A prime, B prime, C prime, in other words, the brown one over here, is a translation of A, B, C, which is the blue one over here. Is that true? No, that's not true. A translation means it would keep its direction. It would keep its orientation. In fact, this would be some sort of a rotation. Okay. A, B, C, A prime, B prime, C prime is a glide reflection. Glide usually is the same thing as a translation of ABC. Let's see number 3. It's a reflection in the origin of ABC. Yeah, reflection in the origin means the same thing as a 180-degree rotation. Is this a 180-degree rotation? Well, xy becomes negative x, negative y. xy. No, it doesn't look. Yeah, it must be a glide reflection. I guess it's a reflection in what, though? That's the thing. It's a reflection in well, it's a reflection that moved from place to place. All right. All right, these are essentially the same ideas. It's a reflection of the x-axis. All right. So I think that's about all I wanted to cover today. A couple of minutes early, but I think we can stop here. Now, If does anybody have any questions on anything really throughout the course, I'm happy to go over anything, from any homeworks or or just anything that anybody wants to discuss. Generally speaking, and this is for those of you that are here, and obviously those of you who are listening to the recording, feel free to post questions to the message board or to email me or whatever it is. In fact, it's better even to post questions to the message board, because if you don't understand something, odds are pretty good that there's somebody else who's not understanding something as well. I'm not, obviously I don't want to sit there and do everybody's homework for them completely, but if there's something particular somebody doesn't understand, I'll be happy to make a little video or whatever it is and try to explain anything that anybody doesn't understand. So please, feel free to take advantage of the resource. And again, I hope everybody will please try to avoid waiting for the last minute to do the assignments for this course. I hope everybody, if you haven't done many of the assignments, you'll really get going, long before the deadline. I really hope everybody will do so. So with that in mind, I want to thank everybody for coming throughout the course. If you're taking finance, I'll see you tomorrow. If not, hopefully I'll see you in future courses. If you're graduating, congratulations to you. And have a wonderful evening, everybody.